Hello everyone, this is online lecture 6 of the course Network Control Systems. Today's title is Retrofit Control for Modularity in Design Part 2. Let's first review the definition of retrofit control introduced in the previous online lecture. A dynamical controller K, which is a map from the local output signals Y, V, and W to the input U, is said to be a retrofit controller if the entire feedback system here is kept internally stable for any environment G bar such that the pre-existing system, denoted by G pre here, is internally stable. The pre-existing system G-Pre is shown by this red box, which is the feedback of the environment G bar and the subsystem G. In the previous online lecture, I explained a state space approach to find a retrofit controller. In this lecture, on the other hand, we use a transfer function approach to characterize the retrofit control from a different perspective. First, the notation and the assumptions are summarized in this slide. As I explained, all systems here are supposed as transfer matrices in the frequency domain. In particular, the submatrices of the subsystem G are denoted in this way, where GWV, for example, denotes the transfer matrix from the input V to the output W. All other submatrices are denoted in a similar way with the subscripts indicating the input and output signals. Furthermore, partial blocks of the submatrices are also denoted in a similar fashion. For example, the transfer matrix from the inputs D and U to the output Z and Y is denoted as like this. Other block matrices are denoted in a similar way. For simplicity, we assume in this lecture that the subsystem G itself is stable. This is not an essential assumption, but it can significantly reduce the notational complexities in the following discussion. Before going to the details, let's overview the main contents of this lecture. The main contents are divided into three cases in which the suppositions of measurable outputs are different. In particular, in the first case, only the local output Y is supposed to be measurable. Under this supposition, I will show a characterization of all retrofit controllers, namely a necessary and sufficient condition to characterize the existence of a retrofit controller is derived. In the second case, the interaction input V is supposed to be additionally measurable. This case is the same as the case considered in the previous online lecture. In fact, we can prove that any retrofit controller, which is a map from YV to U, can be represented as like this block diagram. In the third case, supposing that the interaction output W is also measurable, we will see that more reliable control performance can be realized by integrating a learning technique of unknown environments into the framework of retrofit control. Clearly, the number of measurable outputs increases in the order of case 1, case 2, and case 3. Okay, let's first consider case 1. The main theorem in this case is as follows. Consider the controller parameterization of K like this, where Q is called the Youla parameter, which is a proper and stable transfer matrix. Then a dynamical controller K, which is a map from Y to U, is a retrofit controller if and only if this equality condition is satisfied for the Youla parameter Q. This is a concise characterization of all retrofit controllers, which is given as a constrained version of the Youla parameterization. The meaning of this theorem may not be very clear for you, so I will explain the details in the following slides. Let's overview a standard version of the Youla parameterization here. In fact, if we consider the case of no environment, the problem of finding a controller K is just a standard controller design problem for the plant GYU. Please note that taking the environment G bar as 0 can be a possible choice of environments because the subsystem G is now supposed to be stable. So, the local controller K must be a stabilizing controller for GYU. In particular, this feedback system must be internally stable, namely all 4 transfer matrices here must be stable. Then, we can easily see the following fact. This feedback system is internally stable if and only if this red system is stable. In fact, if this red system is stable, then the 4 blocks here are all stable because GYU is now assumed to be stable. On the other hand, if this feedback system is internally stable, then this red part must be stable. Therefore, the stability of this Q is a necessary and sufficient condition for the internal stability. Furthermore, by a simple calculation, we can see that this representation of Q is equivalent to the representation of this K. So, all controllers K that internally stabilize GYU can be written by this Youla parameterization, where Q is called the Youla parameter representing a stable transfer matrix. Please look at this link for the case of unstable GYU. Next, on the other hand, let's consider the case of K taken to be 0. This corresponds to considering the pre-existing system composed of GWV and G bar, which is assumed to be internally stable. This means that the environment G bar is a stabilizing controller for GWV. So, we can also perform the Youla parameterization of G bar like this, where Q bar denotes the Youla parameter of G bar. In fact, if we apply the Youla parameterization of the environment G bar and that of the controller K, we have this block diagram for the stability analysis of the entire feedback system. Please note that now we assume that G bar is any system such that the pre-existing system is internally stable, which is equivalent to the fact that this Q bar is an arbitrary element whose norm may become arbitrarily large. Therefore, the internal stability of the entire system is guaranteed if and only if the multiplication of GWU, Q, and GYV is equal to 0. This is a sketch of the proof of the stated theorem. Here, I explain the meaning of the derived condition. To do this, let's consider the transfer matrix from B to W here when removing G bar, which corresponds to the interaction dynamics with the environment. Then, such a transfer matrix is obtained as like this, where K is not necessarily a retrofit controller. In fact, the necessary and sufficient condition for retrofit control corresponds to the fact that this red part is equal to 0, which is equivalent to this equality. Therefore, for any retrofit controller, the interaction dynamics MWV is invariant from the original dynamics GWV. From the assumption of the internal stability of the pre-existing system, we know that the feedback of GWV and G bar is internally stable. So, the basic principle behind the retrofit control can be understood as keeping the original internal stability. Okay, let's next consider case 2, where the interaction input signal V is additionally measurable. We can prove this theorem for this case. Suppose that the dimension of the input U is less than or equal to the dimension of the interaction output W. Then a dynamical controller K, which is a map from YV to U, is a retrofit controller if and only if K is given as a multiplication of K hat and R, where K hat is a stabilizing controller for GYU and R is defined as like this. The block diagram of this retrofit controller is like this, which is the same as the diagram derived in the previous online lecture. Please note that the available input ports of U are often limited due to the limitation of actuation. So, the supposition of this theorem holds in many of practical situations. In that case, the retrofit controller is always written in this form. Let's here think about the implication for the state space approach in the previous lecture. In the previous lecture, I showed that a retrofit controller which uses Y and V as a measurement is given as like this, where K hat is a stabilizing controller for this system. This simply means that K hat is a stabilizing controller for the isolated subsystem G, like this figure. In fact, the derived retrofit controller is identical both in this time domain approach and the frequency domain approach. However, the point here is that we cannot say anything about if another retrofit controller exists or not based on this state space approach. On the other hand, the frequency domain approach here can actually prove that no other retrofit controller exists, provided that the dimension of U is less than or equal to the dimension of W. In other words, we can prove the uniqueness of such a retrofit controller. In this frequency domain representation, the resultant control performance can also be compactly written. Consider the transfer matrices from D to Z hat and from D to W hat in this blue system, which are denoted by T hat ZD and T hat WD here. Then, the H infinity norm of the entire map from D to Z is bounded as like this inequality, where gamma hat and gamma check are defined as like this. This bound basically means that if we design a suitable controller K hat for the blue upstream system, then the resultant control performance is improved in the sense of at least the upper bound in this equation. Here I give today's homework. What to do is to prove this theorem shown in the previous slide. Necessary hints are summarized in this slide. The proof of the statement can be constructed by connecting these four facts. Please carefully examine the meanings of these equations. Next, let's consider case 3, where the interaction input V as well as the interaction output W are measurable in addition to the local output Y. In this case, using the measured local data of V and W, we may be able to learn an approximate model of the environment. In the power system example, V and W correspond to the local data of the bus current and the voltage as the signals of interaction with the unknown environment. Let's here suppose that an approximate environment model denoted by G bar APX has been learned from local data such that the magnitude of the modeling error delta is small enough. The objective here is to use this approximate model so that we can improve the control performance in the framework of retrofit control. In fact, using such an approximate environment model, we can further improve the reliability of retrofit control like this. This is the resultant block diagram of the entire map from the disturbance input D to the evaluation output Z. This is actually similar to the block diagram of the original retrofit control, but these two blocks shown in blue and red are actually different. Here, this controller K hat is a stabilizing controller for the feedback of G and G bar APX, where the approximate environment model is used. Also, the modeling error delta appears at the front of this red downstream system. Therefore, a bound of the resultant control performance can be derived as like this. An important fact here is that the modeling error delta is involved in the value of gamma check plus here. Therefore, if we can reduce the magnitude of delta, then the resultant control performance is close to the value of gamma hat plus here, which can be reliably regulated by a suitable design of K hat. The basic ideas behind this generalization can be simply explained as like this. The first point is that we regard delta as a new environment while decomposing the original environment G bar as like this. The illustration is given here. This gray part is the original environment, which is decomposed as the sum of delta and G bar APX. Then we regard this blue part denoted by G plus, which is the feedback of G and G bar APX as a new subsystem for which a retrofit controller is designed. So, we can regard the modeling error delta as a new environment such that it internally stabilizes the subsystem G plus here. The resultant state space realization of such a generalized retrofit controller is given as like this slightly complicated form. For simplicity of notation, I here suppose that the approximate environment model G bar APX as well as the controller K hat are static components, even though they can be dynamical systems in general. This retrofit controller uses all signals Y, B, and W as measurement outputs. The controller K hat is designed as a stabilizing controller for this G+, which is the feedback of the subsystem G and the approximate environment model G bar APX. The state space realization of this block diagram is written as like this differential equation. Finally, just for reference, I explain the case where multiple retrofit controllers are simultaneously implemented. A general network system to control can be represented as the feedback of a system L, which represents the interaction among the subsystems, and the block diagonal system G, whose ice block represents the dynamics of the ice subsystem. For the power system example, L corresponds to the collection of unknown loads and the transmission lines connecting the generators, and the GI corresponds to the ice generator. Furthermore, the collection of the retrofit controllers can be written as this green block, and the controller KI corresponds to the ice power system stabilizer in the power system example. In fact, this block diagram can be regarded as a macroscopic retrofit control problem where the interaction in blue is considered as an environment, and the subsystem G and the retrofit controller K are supposed to be block diagonal systems. From this viewpoint, we can perform similar analysis of stability and control performance also in the case of multiple retrofit controllers. Okay, this is the end of this lecture. Thank you for watching this video.